Our mission is to prepare the next generation innovators, leaders, and change agents. Welcome to the 32nd Global Teamwork event. My name is Renate Fruchter, and I'm the founding director of the PBL Lab at Stanford University, home of the AEC Global Teamwork, and host of this annual event. What is unique about our AEC Global Teamwork is that it brings together students, faculty, and industry mentors coming from 5 disciplines: architecture, structural and mechanical engineering, construction management, and life cycle financial management. Students learn to collaborate in globally distributed teams across discipline, time, space, and culture to virtually design and build university buildings, addressing local conditions. But before we dive into the team presentations, I want to express our gratitude to all our university partners for their support and active engagement over the years. A big thank you to all our industry mentors and alumni who generously dedicate their time, attention, and knowledge to all our students to create a real-world project-based learning experience. Special thanks to our Stanford Center for Integrated Facility Engineering, SciFi, and to our industry partners, DPR Construction, Swinnerton, and HOK, for their continued support and sponsorship. A big shout out goes to our PBL Lab visionary technology sponsors for their generous support that enables us to reimagine collaboration, education, and new ways of working. Integrate data, models, and disciplines, and embed AR, VR, generative design, and optimization in the daily work practices of our students as they develop end-to-end integrated, intelligent design, manufacturing, construction workflows. So our students are invited every year to design buildings for people, questioning what is the future of learning and work. As we shape our buildings, thereafter they shape us. And lately, as we shape our technologies, thereafter they shape us. Addressing in their projects the current climate emergency, coined Code Red for Humanity by the UN Secretary General, as well as reflect in their projects our AEC industry's responsibility to adopt innovative construction 4.0 processes, digitalization, industrialization, prefabrication, and new materials to build more sustainable buildings for current and future generations. So, to address these challenges, students responded to this year's theme, Generative Minds for a Better World. AI, enhanced collaboration, and high-performance buildings. These were supported by 3 specific competition topics. The 90s Sustainability Challenge focused on time and urgency to define their sustainability impact in a temporal dimension. IPD Challenge focused on cultivating a team mindset in support of productivity in the age of construction 4.0, coined T-Mind. And last but not least, the Technology Challenge, inviting the students to connect the dots between innovative technologies, processes, and the buildings that people actually go to work and learn, focusing on sustainable, intelligent supply chain. So this year, we gathered at this annual PBL event to listen to the 3 AEC Global student teams share their projects and team process, and discuss with industry mentors their solutions. So, without any further delay, Central team, the floor is yours.
So, hello and welcome to our spring presentation for the PBL Lab 2025. We would like to introduce ourselves. We are the Central team. My name is Daniel. I'm the architect from Aalborg University in Denmark.
My name is Zacharias. I'm a structural engineer from the Technical University of Denmark.
My name is Michelle. I'm from Stanford.
My name is Angelina. I'm a structural engineer from Stanford.
I'm Alexandra, MEP from Salesian University of Technology.
I'm Lucas, and I'm a construction manager for the Metropolitan Technology University of Chile.
I'm Tasnim. I'm also a construction manager from Loughborough University.
And I'm the last one from the group. I'm Timo, the SCFM from Bauhaus University in Germany.
And these are our 6 owners. For this presentation, we will start with an introduction to the 3 challenges, then followed by general project introduction. Then we will go into the living Oasis, starting by an overview, then building highlights, and ending with construction and finance. And lastly, we will give you the next generation of teamwork and end with a summary.
Yeah, to start, I'll give you a brief overview of our site. Our site is located at UCLA on the west coast of the US. I want to briefly mention that I actually graduated from UCLA less than a year ago, and I grew up in Los Angeles. So it's really got us to know the site well, giving an on-the-ground experience. As you can see, the site is located in a very congested area in Westwood with many different typologies, obviously the UCLA campus, residential, medical, etc. Most importantly, our site has many opportunities. Located on the corner of a busy intersection, our site has the opportunity to become this kind of landmark connector space, as well as surrounded by many greenery that we wanted to highlight. Kind of here's a 3D view of our site surrounded by the different typologies, as you can see. And then while I was home for spring break, I was able to give our team a virtual site visit to understand the site even better. Here's some shots.
And our site biggest challenges are seismic zone, high urban density and noise, but also some natural factors related to climate changes, especially fires, droughts, and high temperatures.
Since I went to UCLA, I was able to send out a user survey to about 30 current and former undergrads and grad students to get understanding of what they didn't like about the current building and what they want for a new one. The key takeaways that they wanted more study spaces, they wanted more cloud rooms, and more integration with tech and sustainability. We mapped out kind of 3 different UCLA personas: me as an undergrad, a student researcher, and a professor, to understand how different users interact with the site, to kind of see how they move differently and see how the space could be used.
Moving on to the first challenge. For future reference, this is our icon representing the IPD T-Mind challenge. And T-Mind is a shared approach to first sustaining a supportive and energizing work culture, learn through understanding each other's to build trust and reduce friction, and also create by pushing boundaries, exploring new tools, and designing solutions that reflect the full range of our team strengths. Our 16-week workflow is best captured by a chutes and ladders analogy, with ladders representing accelerators like AI integration and early goal alignment, and chutes marking pivots and clashes. Still, each turn moved us forward through fun learning and adaptation. And our second challenge for the sustainability time, we're used to thinking of time as a countdown to project handoff, but what if we instead shifted our mindset and time doesn't run out, it keeps looping? And this is our icon for future references. And we reimagined the building lifecycle as 2 interconnected infinity loops, one virtual and one physical, where we build a project twice at least. First, we create a digital twin using data integration, simulations, and collaboration tools to test, iterate, and fail early and cheaply. This enables the physical loop to unfold with clarity and confidence, directly benefiting from insights gained virtually. And it's not a coincidence that our team workflow from the T-Mind challenge maps directly onto the virtual loop. This framework turns every project into an opportunity for circularity and resilience. So the physical loop doesn't just end, it circles back, materials are recovered, data is reused, and lessons carry forward.
for the sustainable intelligent supply chain, we identified two key challenges. First of all, this will be for future reference. How to implement a fast trackable supply chain during the construction, also how to reduce the associated CO2 emissions. To address this, we focus on three strategies. First of all, ensure timely and delivery of necessary elements. Second, the design for prefabricated installation. And the third, but not least, track project progress to adjust the supply chain as we need it. To measure our success, we define KPIs that we will look at the end of the presentation.
Now we have come a long way, so let's take a look back and at our window presentation where we at this time had 4 different concepts. So we evaluated each of these concepts based on a selection of KPIs based on our challenges, user survey, and clients. This resulted in these 4 spider diagrams that evaluated each concept on the 13 different KPIs. And then we ended up with one clear winner, which was the living oasis constructed in mass timber.
Now onto our concept, the living oasis. The living oasis was directly inspired by our perception of the sites, with the very dull and grey intersection contrasted by the very green corner. So we saw this as an opportunity to create a landmark entrance to UCLA by utilizing the existing nature and rooting ourselves in the culture of UCLA and thereby creating our long-term sustainability. So we front-loaded a bunch of our sustainability metrics very early on with these concept goals. I will not present them one by one here, as we will go one by one throughout the presentation. So our massing evolved by firstly placing the building as a climate barrier from the intersection and from the wind. Then we excavated the naturally shaded courtyard to create thermal comfort and for the Santa Ana winds. Then we created the direct sideline to the oasis through the building, created the indoor-outdoor connection to the courtyard, and lastly, we placed the cantilevering treetop for the final building. Now, our concept has evolved through many stages, though the concept itself has stayed relatively the same since the kickoff. The footprint and the axis has been reassessed many times as we went through the iterative process and gained new knowledge. The building itself is placed facing the intersection with multiple different entry points, and the recessed entrance also helps to improve the circulation around the site. You have direct sidelines from all across the intersection, and we added an extra footpath for increased flow. We noted at the virtual site visit that the diagonal access in the context was very prominent, which is why we placed the entrance this way. And this is what our building would look like merged into the surrounding context. This is what the courtyard looks like as you approach from the pathway, sheltering the courtyard. Now onto an overview. Most of our program is based on the idea of the flipped classroom, where lectures are assumed to be mostly done from home, and the university is reserved for more group work, PBL focused group work, mentoring sessions, as well as just a social space in general. The main problem that we found in existing buildings is the lack of occupancy in the auditorium and classrooms for most of the day. So we leveraged this to create dual space co-working spaces. Key spaces in the living oasis bottom floors is the clear entranceway, the lounge, cafe area, the adaptable event space, as well as the courtyard. So given the LA climate, it is a very obvious way to integrate the courtyard even more, which would really help for the client team, sorry. On the basement floor, on the 2-level basement floor, we have the adaptable auditorium, as well as the Fab Lab and a prototyping lab. And on the first floor, we have the entranceway, the exhibition space, and the classrooms, adaptable classrooms. On the top floor, we have the more private space. We have the hot desking, the deep workspace, the focus pods and meeting rooms. as well as a open co-working space and an adaptable classroom. In this section, you can see the different levels of the basement floor, as well as how most of the spaces orient around this double height central space. Now, this openness in the building creates very clear wayfinding, and circulation happens on equal terms for everyone. Here you can see the circulation for the normal. And next you can see the accessibility for people with accessibility needs.
Next, onto our structural system. For our gravity system, we're using mass timber everywhere with prefabricated concrete retaining walls around the perimeter excavation. Then for our lateral system, we are using prefabricated concrete shear walls as cores around staircases and also isolated areas near the entrance on the auditorium. The CLT acts as the diaphragm. You can see the load passed for both gravity and lateral. And then first, for our structural analysis, we assessed the seismic risk of a building. We ran a modal analysis and identified the first 6 significant modes of vibrations. Modes 1 and 2 primarily isolated to the auditorium shear wall, as you can see on the left side, which is expected due to its large ceiling height and lack of CLT bracing. Our main modal participation begins at mode 3, where we begin to see more typical building-wide vibration behavior involving the rest of the structure. Importantly, the fixed 6 modes capture over 85% of the mass participation, representing the building's seismic response. Then we looked at interstory drift ratios and story displacements using 3 different analysis methods. All the methods produce fairly similar results, with response spectrum analysis giving us the highest drifts and ELF time history relatively the lowest. We use the El Centro as the ground rush input.
To give an overview of HVAC systems, as a primary systems, we use photovoltaics and a heat pump, and we also have batteries to store excess energy. And for secondary systems, we have overhead VAV ventilation with jet nozzles in auditorium, and also we have separate exhaust systems for fab labs, restrooms, and battery room. And this is how our air distribution looks like.
Now onto the concept goal of creating a sensory sanctuary for the social sustainability. The architectural expression is experienced linearly, referring to the metaphor of the oasis. We step over the sand dune, then we get the clear sideline onto the oasis. Then we step inside and get the refreshing breeze and the thermal comfort. Then we step ahead and look down onto the oasis with the view framed by the living walls. And lastly, you step into the oasis space, which is a lively indoor-outdoor space.
In relation to our sustainability time challenge, it is important to include the user as well in our building. We believe that an informed user creates a better shared direction between us, the design team, the client, and the user. This is why we have introduced a user dashboard in the entrance of the building. And in order to nudge transformative behavior, we're giving this performance overview to the user, which also includes the building occupancy, the room CO2 levels, and also a green tip of the day to ultimately give the best possible user experience to the user.
In direct connection to the users, our living walls surround the main social area, improve sound absorption by up to 60%, and enhancing indoor comfort as well. They also sequester around 1,000 kilograms of CO2 per year, and with this they contribute to a more sustainable environment. And financially, the system requires an initial investment of 200,000 with some ongoing replacement costs, but still for the visual quality and positive impact on the users, we consider it as a valuable investment that brings life into our building.
Now, our material choices help to provide a healthy indoor environment. We have a very thick envelope, used the installation as hempcrete to optimize the ventilation system. We've used hempcrete for its properties to being carbon negative, not releasing any pollutants to the indoor environment, being biodegradable, and also for its acoustic performances. We've used Accoya for many of the same reasons, and also its high durability and its patina, which supports the architectural vision. Also, we have used wood on the interior to help enhance the well-being and productivity of its users.
And to ensure the best possible air quality in our building, due to Santa Ana winds and fires, we use mechanical ventilation with two-stage filtration with MERV and HEPA filters. So proper filtration with regular filters replacement allows us to provide an even better sensory sanctuary experience and users' well-being and health.
Next on to the organic structure design concept goal. We wanted to create a building that draws inspiration from nature's organic shapes while remaining structured, efficient, and strong. We're looking at the evolution of a structure system. We most importantly wanted to create an even grid, but oftentimes this didn't align with either architectural or adaptability goals. As we progressed, we continued to work with MEP and architecture to create structural systems that were fully integrated for both our mass timber and steel options. Looking at these options, we identified key performance categories and identified which was stronger. Steel had stronger structural strength, fire resistance, and repairability, while timber had stronger sustainability and constructability. Ultimately, we wanted the timber option because of its stability and ability to design for disassembly.
And here are the live loads we used. We simplified our unique loading conditions to ensure that the structural system doesn't constrain future flexibility and adapting the rooms to evolving user needs. And our foundation uses a combination of prefab retaining walls and isolated concrete footings at 2 different sizes. On level 1, the main areas to note are first the collaboration with Arch, MEP, and CMs to rotate the grid around the entrance to enlarge and better frame the views to the central courtyard. And there's also slanted columns around the perimeter to support the cantilevers.
As mentioned, we rotated the grid of the entrance. Initially, a west-facing entrance had 4 sight lines into the Oasis courtyard, but after a virtual site visit, we noticed this kind of natural diagonal entrance from the busy intersection. So we shifted the entrance the grid at 45 degrees to create this clear sight line.
And then also level 1 with spanning 2 stories is our key living tree feature with curved columns that further our Oasis concept and also structurally maintain our main beam member sizing by reducing this longer span length. To actually construct our biophilic tree, there was a lot of coordination with CMs to determine the logistics and locations for special connections for the slotted steel plate and dowels to allow for manufacturing, delivery, and erection of these double height slanted or curved columns. And on the top level, the beams are value engineered to reduce unnecessary material and costs.
Now onto our transgenerational spaces concept goal to create value for people in the long term. We have these adaptations to the auditorium space. It can either function as an auditorium seating 180, a fully open event space, or a classroom. This can either be PBL or traditional system. The auditorium integrates tech to create a digital twin classroom for online lectures. It also has a conferencing system and multi-projector system, which integrates well with the event space to provide with 360 technology. What makes this whole system possible is the tiered retractable seating, the multi-directional operable walls, as well as nested furniture and a dedicated storage space.
And as we mentioned, the auditorium is ventilated with jet nozzles. Supply system is hidden behind the wall, while return is located on the opposite side under the beams to avoid clashes with structure. And here we show how ventilation works in different variation of adaptable spaces. So the whole system is designed for the highest occupation. And since it works in variable airflow, it is possible to adjust the airflow for this smaller classroom case. And also in the case of an enclosed auditorium, the space that is outside, it's not highly occupied, so it can be balanced by ventilation from the corridor as it's shown on the right side.
And the area shown here in orange serves as an event space with an estimated annual rental income of $100,000. Including minor security upgrades for the auditorium and the staff in it. The total life cycle cost over 24 years is around 2.8 million. And in addition, so with this, we gain a lot of extra income throughout this event space. And additionally, orange marked rooms will support events at storage or changing room areas, or like a multifunctional room will also be offered to use CLA for extra meeting space.
As part of our IPD challenge, we believe in data-based and informative decisions, which is why we have always performed these studies in order to determine the value of each variation of a concept. The big revelation then came when we realized our auditorium study and our cantilever study were not separated, but they were inherently linked. So this made us rethink the entire cantilever, and by extending the long span in the auditorium, we could more or less reduce the cost of the cantilever significantly. And then the auditorium has been through major changes throughout, but a focus on integration and collaboration has always been the centerpiece throughout the entire process. A key example of this was working with Arch to reduce the live load on top of the auditorium, right here. And as well working with the construction managers to look at the connections and design the connections both for transport and to optimally design it for both shear and moment.
As mentioned, the beam pieces will be delivered and assembled on site. Since the auditorium beam's total span is 84 feet, we plan to move and construct using a tower crane, which has an arm extension of approximately about 131 feet. This is so that we can construct well on site.
And directly in front of the auditorium, our cafe is generating about 7,500 in annual rent with just the 6,000 initial investment and a life cycle value of around 109,000. It serves both indoor and outdoor areas from the auditorium, as well as supporting events there and foster informal exchange for daily students or visitors. And beyond the rental value, it's strengthened also long-term social sustainability and the user well-being.
Now on to creating the optimal learning environment. We know from the user survey that the users want more collaborative spaces. So we tried to focus our plans on creating a diverse learning environment, for example, inspired by cases like WeWork. We have social spaces, collaboration spaces, learning spaces, and the more personal spaces on the top floor. Now for the flexible classrooms, we have two sections, and we use this center folding wall system. Now specifically for this space up here, it can adapt in 2 dimensions to a co-working space, one big classroom, or 2 smaller classrooms.
And because of the folding walls, which have special structural requirements, we placed main MEP ducts in the corridor under the beams. And to hide the visible crossovers of the ducts, we used suspended ceiling on the second floor to provide a better aesthetic feel of the building.
And to meet our users' need for outdoor study spaces, we have designed the courtyard as an extension of the indoor environment. And this is what you see right here, where additional study spaces have been introduced outside. This concept was inspired by UCLA's bomb shelter, a very popular student study area, which we were able to experience during our virtual site visit. This courtyard has also seen rapid evolvement, especially trying to reduce excavation while simultaneously optimizing the comfort area. A major constraint here has been the site limit. We have had a hard constraint of 30 feet above the ground, which has forced collaboration between all disciplines. And one way we have reduced and tried to optimize a building for this was after our concept presentation, we reworked our entire framing system and reduced the span. We introduced double span CLT slabs, which we were then able to make the MEP go between the beams, perpendicular to the beams, which resulted in an excavation reduction of over 3 feet and thus a cost reduction of $90,000.
And to kind of extend previous slides, we want to show the complexity of our building. So here is an isometric view of MEP model overlaid with structure. and also full floor sandwich of our building. And for the self-sustaining goal, we implemented solutions that allow the building to be as independent as possible with highly efficient systems. And in MEP systems, we also focus to provide the feeling of living oasis with thermal sensation. So our goal was to create at least a net zero building. And here we show what is our building performance, how it looks like now. And in reference to the long-term sustainability impact of our building, we decided to produce energy from photovoltaics on our roof. And the excess energy is partially stored in batteries, giving us backup energy for several hours. And the remaining energy is sold to the UCLA campus because they are currently using cogeneration to provide electricity, but it's enough only for 80% of energy needs of the campus. And also to reduce energy consumption and related to that costs, we implemented night cooling.
Okay, and so to realize the living oasis within a harsh concrete dominated environment, we used the photovoltaic to implement a PV system that enables almost 90% of self-sufficiency, creating an almost independent island system in this area. And this transforms the surrounding concrete desert into a vibrant landmark with our PV system. And with the selling to the UCLA, rather than the less green local grid, we're generating additional 100,000 in profit, and with an initial investment of 315,000, the system yields nearby 1.1 million in revenue and savings throughout the complete life cycle. And with this, we are reaching a break even after just 8 years.
Also, in response to future climate changes, mostly related to droughts, we will use water as a long-term sustainability solution. And for that, we have planned 2 underground tanks for grey water and rainwater. And rainwater can be used for hand washing after proper filtration and disinfection, while the purified grey water can be used for toilet flushing and greenery irrigation. And we also decided on a unit to produce drinking water from moisture in the air, which can provide fully the cafeteria needs, as well as some tap water amount. And to reduce water needs even more, we use vacuum toilets and water saving taps. So with all of these solutions, we have reduced the amount of water that we need to purchase from the grid by 76%.
To extend even further the living of the oasis, we are improving air quality and acoustic comfort with the smart sensors from AirThings.
So we use this data in 2 ways. First way is for HVAC automation, which means that the system monitors air quality and adjusts ventilation only when it's needed. And the second thing is noise mapping to help identify areas to future acoustic improvements.
And with this investment, the system delivers 32,000 lifecycle value, but for a long time, it's good for sustainability as well.
And so for part of tracking our sustainable goals, we have done several iterations of STV. And the first one was made with just preliminary assumptions. And the next iteration was made with more accurate data and TVD input. And after that, we noticed that we have a problem to achieve the targets, especially for water. So we decided to implement such solutions as water harvesting and water saving restrooms fixtures. And with this, we reduced water consumption, but it was still over the target. So we set up a team meeting to discuss this STV. And together we found some mistakes that had a huge impact on the results. And as a final result, we are currently even below the established goals.
Now, the building itself tries to abstract the tree with the canopy and the leaves blowing in the wind and the cantilever. On the inside of the top floor, we try to emulate the sense of being inside the Oasis canopy. And the evolution for this facade happened through many different stages, and it happened collaboratively to increase the SDA KPI. Initially, it was supported by the metaphor from the architect. And then later on, the MEP noticed the benefits it would gain from the dynamic daylighting. Then at a team meeting, we were informed that this would be way too many parts by the CM. So we condensed it a little bit to now be a 3-part dynamic shading system. Next, we were informed by the client and the LCFM that this would be way too costly, both in the short term and in the long term. So we collaborated to evolve it to a static facade instead of a dynamic facade. Now, this led to an evolution of the static facade system that started with optimizing each room for the optimal shading angle, a UDI study. Then we put it into Grasshopper to develop the organic shape, where we first optimized for the daylighting and then next optimized for the view. And this process altogether saved us around $400,000 and improved our SDA to be 77.4, and in total, a 91% reduction in parts. Also for the daylighting, we implemented solar tubes in underperforming areas, and this was mainly to reduce the operational costs and the energy needs.
Now onto the concept goal of optimized construction. For this site, several factors had to be considered for pre-construction and on-site construction. Some of these include that we have a nearby hospital, so we had to have careful management for noise and traffic. There are also trees that we didn't really need for our design, so we thought about removing them. Our site is quite tight, so we did a 4D simulation using the local truck turning regulations for Los Angeles, as you can see on the left. This is so that we can ensure that we've got feasible maneuvering. So we decided that we were going to do tree relocation rather than just removing the trees. After reviewing the trees on site, we realized there were some live trees. We want to relocate them either to UCLA Botanical Garden or to the National Cemetery. This is so that we can preserve the biodiversity and the carbon storage.
So for the equipment, we consider the aforementioned crane, as well as an excavator with a 1.3 cubic yard cubed bucket. It has a maximum reach of 20 feet, allowing us to work comfortable in the excavation. Also, an extendable articulated boom has considered for transporting small parts. This boom was intended to transfer materials from the lower to the higher levels.
For our site logistics, we've located our storage and offices on the northern side because it's the most quietest area during construction. We've also done a recycling and waste near gate 1, so this is easy and regular removal. And we've also made a temporary road through the actual site so that delivery and access.
The structural and waste management plan was developed to support sustainability under tight timelines. Packaging, scrap, and surplus material are sorted on site and sent to recycling, potentially generating income for minor site needs. Waste Waste is tracked using departure sheets for each vehicle to estimate total waste generated. Further details can be included in the appendix. So here we can see a simulation performing in Fuser. The optimized construction schedule was imported from AEC and the model exported from Revit was incorporated. We can take into account that the largest flow of tasks occurs between the completion of the structure and the start of the interior works, which includes tasks such as the installing interior ducts and interior partitions, walls of the building. For the concept goal of local resources and resources, we also have developed a kit of parts. For during the design, architectural elements were minimized to the 12 types, identicals in materials and different only on size. The structural elements also were reduced to 6 elements in total, varying only in length. The key parts include brackets and connections plates based on the shipment type. Coordination was done by manufacturer, with quantities calculated using the Rotoblast spreadsheet.
To our concept goal and our goal of sustainability and time, we aim to have our main substructure suppliers within 100 miles. This is so that we can reduce our carbon emissions. Also, with our other suppliers such as MEP, temporary facilities and equipment, we have made sure that it's all within a 50-mile range so that we can reduce our carbon emissions. So while looking at the traffic around the site, we wanted to avoid site delays due to any heavy traffic. So we decided that we're not going to be going through the route of Westwood Boulevard for deliveries. We've also looked at time, so we'll be avoiding peak times such as 12 to 2 p.m. and 5 till 6 p.m. because that's where we found it had the most heaviest time.
To optimize construction, we use technologies for greater speed and accuracy. We use Doxel AI as a power AI tool. Doxel AI uses AI-powered cameras and scanners to track construction progress in real time. It compares actual site conditions with the project schedule and view models. This impact in the supply chain in 4 key points that provides real-time visibility to detect delay early, enables better scheduling of material deliveries, reduces waste and rework by catching errors sooner, and also improves coordination between on-site progress and off-site manufacturing. For the construction budget, we reached a final total of 17.9 million, with the largest cost being the structural, utilities, and furnishings. To achieve this, we track design changes. We track the design changes, allowing us to see the major changes with their respective dates and how these changes affect the budget. We also present the workflow for delivering an intelligent supply chain. It begins with the Revit model, followed by the BIM execution plan to ensure best practices and minimize conflicts. Model data is transferred via add-ins or IFC exports. Architectural elements are sent to CodeBI for parameterization and also finalization, and also for the CO2 equivalent estimations. For the construction simulation, we'll start in MS Project, and this is optimized in Alice and finalized in the future for the logistics simulations. We finalize elements are then exported into manufacturing software for production.
We had 3 main milestone goals, but as a team, our main one was to be able to construct our building within 9 months so that we could receive our 2% premium. Initially, we had produced our schedule on Microsoft Project, and we ended up calculating 10 months for this building to be complete. So then we moved on to Alice, and we exported our previous file onto Alice just to see how efficient the construction schedule could be. We applied different scenarios and we were able to complete our construction within the 9-month range, which we wanted, which was a great, we would be able to achieve our 2% premium, which is good for us.
To create prefabricated interior partitions, we use CodeBI to panelize elements exported from Revit via IFC. Then these results were imported into Revit for integration. CodeBI also provides material quantities and CO2 data, helping us to reduce the emission up to 52% in these items. Here you can see how it's developed the information and how we were able to reduce the amount of CO2 equivalent for partitions and exterior walls. Also for the definition of the elements, we organize by construction sectors the whole project, each aligned with its specific methods. The model elements were grouped into sets using custom parameters. And And then these models and parameters were uploaded to manufacturing with the scheduling data from Alice, and we were able to process, allowing us to confirm orders for coordination and plan delivers on the site.
Yes, and let's take a look at our next concept goal, design disassembly. So in an ideal world, we would never have to tear down a building and they would last forever. Even though we're still trying to optimize the longevity of our buildings, we still must consider an inner life for our building. One aspect of this is design disassembly, where we have optimized and used aluminium connections for our beams to columns, as well as our rotoblast ring to both design assembly and maximize reusability. This is the same for our CLT connections for the same principles. But we are at a stage in our industry where DFD, adaptability, and recycling is simply not sufficient anymore. So even though something is designed to be reused, it doesn't mean that that's actually going to happen. So how do we ensure this? First of all, we look at the time frame. We extend our time frame from one building to multiple building lifespans. But then the question arises of how we're going to optimize this transition zone. And of course, as the question states, how we can design both for the present and for the future building. There are quite a few challenges with directly reusing members, especially responsibility issues, but we are solving this through structural health life monitoring. And we are placing key members and analyzing key members throughout lifetime. And the end goal here is that we can now document and guarantee that the structural health of members, which allows us to reuse them and sell them at a later point. There's quite a big impact of this as seen by this graph. You see an initial increase in the red of the environmental impact of using structural reuse, but the huge decrease when designing for the next building. So by introducing this time frame of the next building as well, we are actually seeing a quite significant decrease in the overall environmental impact through multiple building lifespans.
And even if the resale or the resale of use of the structure lies far in the future, it increased the resale value up to 60% and extend the building's lifetime. And at the same time, it preserves embedded carbon and material value, and it making a long-term sustainable strategy for us. And coming now to the financials and the life cycle stuff. We tried to achieve a good LEED certification, and throughout our design process, we consistently focused on LEED criteria and earning significance point there. And in the end, we're on the track to reach LEED Platinum with 83 points. And with this, we're enhancing both building value and image. And for integrating our own disciplines throughout the project, we collaborated closely as a team using a clear structure and shared an Excel, so an Excel template with all the costs and leading to a complete AEC model and cohesive building concept. And with the rented spaces in the complete project in our building, we provide valuable additional income, and the event space contributes 2.8 million alone, while the cafe and supports or additional rooms at a smaller amounts, but even that will help to cover future replacement costs across the building, and all these income from the rent increase directly the ERR by 2.9%. Here, as you can see, the total construction cost, like Lucas showed us earlier, and with an interest together, we have approximately 33 million. And with this, we're leading to the next slide with the life cycle cost development. Because of the higher costs on the building and construction side, also, as you can see here, the life cycle costs increased a lot. But an instance for the last sector with an excavation reduce and the facade reduced the cost around 2-3 million. And yeah, with the financing comparison, with an all interest rate approximately between 2.3 and 2.4% between all those banks, we focused on one bank because it's standing out with 4.3 net present value in millions, and with an ERR of 9.6%, sorry. Why we're picking this? Because with a 4.3 net present value, we are getting the most out of the project, but also with the ERR and high in value number, we are getting it a lot faster back, for instance, as the X bank. And for the internal rate of return in detail, throughout our timeline and the main points and dates we had, that was an up and down, as you can see here. And it has an impact on costs implementing like PV panels or water system. And in the last step, as you can see, we get a lot of improvement on the internal rate of return because of the direct selling from the PV and the water savings with our systems.
Moving on to workflow innovations. As a reminder, this is what our team workflow is modeled as, a Chutes and Ladders game. And digital integration lets us fast track traditional steps. So climbing up the ladder means first, onboarding, second, choosing a specific tool for a specific task, 3, critiquing outputs with human touch, 4, making corrections, and 5, sharing decisions transparently. We documented these ladders with first an onboarding log to check how long it takes us to learn versus how long we use it for project work, and if we've actually saved time by using this tool. Second, we have a more detailed and rigorous tracker to capture the what, how, why, when, and so what. It logs tool timelines, input to output ratios, input to post-processing time ratios, and even compares the carbon cost of AI queries to the carbon savings they enable. We took our Naali pool planning data and also our tool to tasks to impact tracker data and combined the two through a database called Airtable, which is even more powerful than either alone. And our tool to task tracker serves as training data for a small but industry-specific language model that suggests tools for Naali pool planning activities, and activity statuses update weekly from pool planning exports with sync timelines for consistency. Our data revealed clear usage patterns. Tools like ChatGPT, Google Forms, and BIM 360 supported daily workflows, while others like D5 and SketchPro spiked near key milestones, showing that they're best suited for more specific uses. This insight helped us tailor our tool strategy by aligning tool selection with task type and project phase. And then looking more specifically at SketchPro, it was initially ruled out for concept inspiration due to unrealistic generations and high post-processing needs. So we did not check the use again button in our tracker. However, we did switch strategies and later re-implemented SketchPro, but this time for upscaling Revit renders, which we loved and then also documented. In our phase-based toolkit strategy, we found that tools introduced 2 to 3 weeks before heavy use worked better than last-minute rollouts. Combined with our onboarding records, we have clear data on how early and how long onboarding should be, and then early exposure helps us reduce adoption friction and ensure tools were proactively planned for. And here's a more detailed breakdown of each use case and the tools used. And then also our carbon tracker pushed us to evaluate not just the outputs of our tools, but their environmental trade-offs. Though full data wasn't always available, we developed a framework to track both the costs and savings where possible. For instance, using format-informed material decisions that led to an estimated 1,400 ton carbon equivalent reduction, showing how digital tools can actively shape our more sustainable design decisions.
Yeah, another thing we're tracking is productivity. After each meeting, each team member fills out a productivity survey asking how long the meeting and what the meeting was for. As you can see, we met many times, mostly team meetings and sub meetings. Another thing we asked in the tracker was how efficient the meeting was in terms of time and how effective the meeting was in terms of what was done, and then what needs to be done next. We don't want to be 100% productive because otherwise we wouldn't be having very fun and we wouldn't be learning. So our ideal range is about 7.5 to 8.5. Lastly, we rate the vibe of the meeting, how much fun we had, because productivity includes fun. We were the most productive when the vibes were the highest.
And then during this last project development phase, we have been using KPIs and a KPI dashboard to first of all establish a clear project direction for all teammates and especially assess the impact of design changes and variations in design. These KPIs, they were developed based on our challenges. Then we got our client input, set our KPI targets, and throughout this process, we have been updating them weekly to track our process and how we are doing. This is how the KPI dashboard looks, where the x-axis on each graph this represents the time, and the graph represents the performance itself, with the quick overview given by the colors of the numbers. Going through the 4 categories, we start with the supply chain, where we see we're hitting all 5 targets. Some have decreased a bit, and some have been on target the entire time. For our T9 challenge, we are hitting the targets except for the clashes, which is only resultant of how our detailed our Revit model is at this point in the process. We are hitting all targets for our sustainability and also actually by quite a big margin. So in this manner, we are doing exceptionally well. Lastly, for the financial statements, since we're not quite hitting for maintenance cost and total asset cost, but since our IRR is this good, all measures are considered good.
Next, we'll quickly give an overview of our challenges again to show that we have been keeping them in mind the entire length of the project. For the first challenge, the IPD Team Mindset Challenge, we were using the chutes and ladder process to think about team workflow. Obviously, we start with a very big idea without different concept goals as we've been presenting throughout. And this has kind of helped us think about our process throughout to be able to keep moving through the ladders. Then we have the different workflow integrations that help us create a smooth chutes and ladder process. And then lastly, we have our different metrics that we are tracking, like AI usage and productivity.
Our dual infinity loop leads to 3 core strategies for the sustainability challenge. The first, user focus and flexibility, makes buildings more useful, more often, and also more socially sustainable. Future-proofing through modularity and open-ended programs means that the building evolves with changing needs. And also our structural reuse through DFD ensures materials live multiple life cycles, so looping through that infinity loop more than once. And this is how we move from a linear timeline to a regenerative circular building process, digitally and physically, and with our T-Mind.
The technology challenge, thanks to the technologies we applied, we were able to improve the construction time by reducing the gap between tasks. We optimized also the materials, achieving a lower CO2 equivalent emissions, and we were able also to generate an on-site delivery schedule, which can be modified according to the needs of the project.
And this entire process has been an incredible learning experience, and we have really been able to push each other to deliver our next generation of engineers and coming together in this scenario. In addition to this, we also want to thank Renate and our clients, and especially a big thank you to all our mentors who have been pushing us and helping us all the way through to reach a higher level. So once again, thank you so much for all the help, and thank you for listening.